Okay, I hope you can switch your brain from exam 1 to exam 2. This is the second lecture on Thévenin and Norton equivalent circuits. Now, we're going to solve this example just to refresh our memory. And we're going to start by calculating the Thévenin voltage, VTH. What should I do to this circuit if I want to calculate V Thévenin? First,
Kill the
dependent?
or is it independent?
Kill the independent source, right? Shorted? Nope.
This one should be a Y.
If I want to calculate V Thévenin?
Oh, feet. I thought we were going to do R.
Not R Thévenin, V Thévenin. What should I change? Nothing. And where is V Thévenin? Across the terminal A and B, right? Is there any element that I can remove from this circuit safely? 10 ohm resistor. The reason? There's no current through going through that. So do you agree that this is V Thévenin? Okay. Then how can I calculate it? Yeah, let's find I. How? So we can just write a KVL, right? Around, you only have one loop, one mesh. So just write a KVL around it. KVL around or at, and let's label the current through the loop. What should I call it? Is it okay? Because there is already one I in your circuit. Can I call it I? It's consistent, but I want you to check it, okay? If you're by default going for I all the time, check that there isn't anything inconsistent with I. Fortunately, that I is exactly consistent with our assumption. So, negative 20 volts plus 6I. What's the next KVL term? Minus 2I plus 6I is equal to 0. And from here, I have I 2 amps, which makes V Thévenin two amps times 6 ohms, which is 12 volts. Any problem? How about I Norton? What can I do here?
That's when we can follow R.
No, I'm going to calculate I Norton first. Sorry? But I don't have RTH yet. So if you want to use that formula, VTH is equal to RTH times I Norton, you need to have two of them, right? But you only have VTH so far. So how do you calculate INO? What's the definition of INO? Short circuit current, right? This is INO. You remember that? Now we have to calculate that. What do you suggest? Sorry? Which one? The 20 volt voltage source? You want to source transform? First of all, you know that you shouldn't touch any sources. Everything should be alive, right? You don't kill anything in I and O calculation. Okay, so how do you handle this circuit? I and O is the unknown that you're after, you're interested in. Let's do mesh. I'm gonna call this I1 and the second one, you can call it I2 or I and O, right? It's exactly your I and O. Let me choose the capital for the first one. Seems more reasonable. And then you can go ahead and start writing KVL. But before doing that, I'm going to do something on my circuit. Can you guess what? Some very minor simplification. Sorry? Simplify 2I. Do you see that? And do you guess why? It's going to appear in my equations, right? So if that's part of my equation, I will end up having 2 equations and 3 unknowns. But if I can simplify it on the circuit, then I will get rid of I in my equation altogether. So what can I write instead of I? So 2I1 minus I and O. This is something that I really prefer to do on my circuits before going to the equations. Okay? Now let's write KVL at I1. Negative 20 volts plus 6 I1 minus 2 times I1 minus I and O plus 6 times I1 minus I and O equal to 0. And KVL at I Norton, which is 6 times I Norton minus I1 plus 10 I Norton is equal to 0. 2 equation, 2 unknown. Use your calculator and tell me what the answer is. I'm only interested in the second variable of your calculator, not the first one. I'm looking after, I'm looking for I and O. .882 amps. Good. Now, how about RTH? Do I need to analyze a new circuit for that? No. Based on the equivalent or based on source transformation concept, I can write RTH is equal to V Thévenin over I Norton, and it's equal to, what was V Thévenin? 12 volts divided by 0.882 amps, and I have it as 13.6 ohms. Nothing new, right? We knew that in from our first lecture on Thévenin circuit. But what if we want to calculate RTH directly? Okay? So we don't want to calculate VTH and I and O and then divide them. We want to do it directly. What's the first step that we do in this circuit? Get rid of all the independent sources. So I replace the 20-volt voltage source with a piece of wire, short, like this. I already replaced it. And then, what do you do usually? Try to combine the resistors and all, and simplify the circuit, and you find one resistor. Can you do it in this circuit and tell me what the answer is? Combine the resistors and tell me what the equivalent resistor is. You did it in the previous lecture. Well, what's wrong? Is there something in the circuit that buzzing you? Can you combine resistors and dependent source? How? That's a dependent source, that's a resistor. How are you supposed to combine? You can't. So if we want to calculate this directly, we can't, right? There's no way that we can just combine these resistors together and find a value of equivalent or Thévenin resistance, okay? Now, let me, before answering that, what's wrong in that circuit and how we can resolve it, let me ask you this question. First of all, let's give you a very simple example, that circuit. We want to find the equivalent or Thévenin resistance from across the terminals A and B. What's the first step? Short circuit the voltage source, right? We did it here. Now you can easily combine them. Do you agree with that? In this circuit, can you tell me what is REQ? REQ is equal to R1 in parallel with R2 plus R3, right? Whatever value it has, you can find the value. Okay, so can someone explain or can someone define the meaning of equivalent resistance? What does it mean? Why are we after it? Why is it important? Because, yes, you can replace an entire circuit of resistors with just one resistor. And the thing is, the promise is that the rest of the network, the rest of the circuit is going to behave the same as if the original network is connected. Okay, so nothing is going to change. Now, let me remove this and let's call this current I prime T. Okay, consider this the circuit that you had. Okay, I've placed it inside a transparent box. I'm going to call it a black box or red box, okay? Whatever you prefer. And I'm connecting, I have connected that to a voltage source with the value of VT. And you can assume that VT is some value, for example, 10 volts. The same here, 10 volts. Okay? So I can see inside the box and I can see all the resistors and everything. And I've connected to a 10 volt resistor, 10 volt voltage source, sorry. And I'm going to measure IT. So I'm going to measure IT and find the value for that. On a separate case, instead of putting the whole network inside the red box and connecting that to the voltage source, I'm going to find the value of the equivalent resistor, and directly connect it to the voltage source. Okay? So since I can have access to the box, I am seeing it, I can calculate it. Okay? This one, you already told me, it's R1 in parallel with R2 plus R2. Whatever that value is, find the resistor from your kit, from whatever supply that you have, and connect it to the voltage source exactly equal to 10 volts. And then again measure the current. Now, based on the concept of equivalence, can you tell me what's the relationship between IT and I prime T? If they are not the same, it means that your circuit is not equivalent. So they should be the same. Otherwise, equivalence doesn't make any sense. So IT should be equal to I prime T. Did that make sense? Did that argument make sense to everyone? If the voltage sources are the same and the network is equivalent to REQ, then the current should also be the same. Right? Now, okay, so in the right circuit, if I divide VT by I prime T, what's the value? Do you agree that it's REQ based on Ohm's law? Everyone? If I divide VT by I prime T, it will give you REQ. So do you agree that in the left circuit, if I connect a voltage source to the terminals of an unknown circuit, filled with thousands of resistors and dependent sources, and I apply a 10-volt voltage source, or any value for that matter, then I measure the current that's going into the network by some ammeter, multimeter, and then divide VT by IT, it will give me the equivalent resistance. Right? Do you all agree with that? If the whole network, in fact, can be replaced by only one resistor, and that resistor is REQ, do you agree that Ohm's law should be applied to that REQ? So meaning that if I divide VT by IT, it should give you REQ value. Okay? That is a very useful method to find the equivalent resistance from across the terminal of a network. The network that has dependent sources and resistors in it. Okay? So this is the summary of our discussion. Now, look at the second pair of circuits, the bottom ones. We sort of found our way through proving why the first one is making sense. Now I'm going to ask you why the second set of circuits, the bottom ones here, why are they valid? Can you, based on some concept that we've covered in our lectures, tell me why the second set is a direct result of the first pair of circuits? How can we go from the first two circuits, the top ones, to the bottom ones? Source transformation, right? You're technically doing a source transformation, so the bottom circuits are also valid. So what does it mean? It means that we have a very powerful method to find the Thévenin resistance or equivalent resistance across the terminals. What is this method? It's called the test source method. You either connect a voltage source or a current source to the terminals. Then you either measure the voltage or current and then divide the voltage by current, and it will give you the equivalent resistor. Okay? Now, when I say measure, I mean in the lab. But if you're doing it on paper, it's called calculation. So you just connect a voltage source across the terminals that you're interested in, define the current going into the network at some IT, VT and IT, and then we're going to do some example, and you're going to see how it's going to go. Just one more question. Do you know any device that actually does this? Someone said it. I heard it. No? Yeah. Does this apply a voltage and measure the current and divide the voltage by current and gives you the value of the equivalent resistance? Multimeter. That's exactly how it does it. It applies a small voltage across the terminals of the circuit that you've connected the probe to. It measures the current that goes into the circuit and then divide the voltage by current. That's exactly how it does. Okay? And my last question. The test voltage source, does it matter if I apply a 10 volts on 1 volt or 1000 volt? Will that change the equivalent resistance or no? It shouldn't, because equivalent resistance is for a circuit that this multimeter is not part of. So it's not logical if connecting that changes the equivalent resistance. So does it matter what voltage I apply across the terminals? No. So what value do you suggest we apply from now on? 1 volt. Let's make it easy. Don't apply 0. I know it's easier, but you're short circuiting. Okay. There is something wrong in this note that I'm going to change it. Not wrong per se, but not very complete either. So let me first fix it, and then I'm going to read it and highlight it. So in order to find the equivalent resistance across the terminals of a first eliminate all the independent sources. Then, if the network is made only of resistors, we might be able to directly find R Thévenin. It's not guaranteed. I'm not sure if you have that on your web board. Sometimes only resistors, okay? Not even any dependent sources. Sometimes only resistors can be arranged in a way that there is no way you can combine them, either series or parallel. And you have to apply this test source method, okay? So remember that the fact that it is only made of resistors doesn't necessarily mean that you can just combine them. Now, if the circuit also has dependent sources, or if it is not possible to use resistor combinations, we have to use the test source method. Okay? Let's go back to our example. Here it is. You know that we calculated our Thévenin indirectly using V Thévenin and I Norton. Now let's do it directly. We're going to apply test voltage source first. So what should I do? I connect the terminals to VT. What should I consider as the value for VT? 1 volt. And this is your IT. And now I'm going to analyze the circuit. Can you tell me what the goal is here? What we want to calculate in this circuit? The Thévenin resistance is the ultimate goal. But from this circuit analysis that you see on the board, IT, right? Why? Because after we calculate IT, we can divide VT by IT, and that will give you the Thévenin resistance. So that is your goal. Okay, how do you handle this? Let's do mesh. I'm going to call this I1, and I'm going to call that I2. Remember, you can't label the second mesh as IT because that's the opposite direction, right? Okay, let's write KVL. Before writing KVL, again, is there something that we can do to simplify the circuit in terms of KVL equations? Yes, instead of I here, 2I, I can write 2 times I1 minus I2. Do you like that? So negative 20 volts plus 6I1 minus 2 times I1 minus I2 plus 6 times I1 minus I2 is equal to 0. KVL at I2, 6 times I2 minus I1 plus 10 times I2 plus, what's the last KVL term? 1 equal to 0. And from here, I can find I1 and I2. I don't care about I1, I only want I2. What is the value of I2? Use your calculator and give me the value of I2. Rating. Nope. Someone else? No?
Are you asking for IT or IT?
Whatever. Either one. Oh.
809.
Oh, yeah. Probably the values that you have is there's a huge, very unforgivable mistake in this circuit. I forgot. You kept the independent source in the circuit. Here, that's the problem. Whenever you want to calculate Thévenin or equivalent resistance, that's the first absolute step. Get rid and kill all the independent sources. I didn't, right? And that wasn't a part of my act. I genuinely forgot, okay? So yeah, remember that. First, eliminate all the independent sources. So I'm going to replace this with a short circuit, and I'm going to remove that 20 from my KVR. Can you tell me now? 0.0735 I have, yeah. And since this is I2, what is IT? IT is negative I2, and it's equal to 0.0735 amps. And what is R Thévenin? It's VT over IT, which is 1 volt divided by 0.0735 amps, and the value that I have is 13.6 ohms. Anything wrong? Okay. Let's do test current source as well. So I connect a current source here, then I define this voltage as V test and this one as I test. What should be the value of I test? IT, 1 amps. And what do you suggest we do for this circuit? Do you want nodal or mesh? What do you want? Nodal? Let's do nodal. What should I call this red node?
Node 1.
VT. Do you see why? Okay, if you label it some other way, it's not wrong. You're just adding one variable to problem. Then I have this guy, and also I have this guy. Nodal is awful, but yeah, anyway. Here, I mean, it's not very good, but okay, let's call the pink one in the middle, what should we call it? I'm gonna call it V2 and the other one V1. Anything wrong? Okay, so let's write KCL. Where should I write KCL at?
All the nodes.
Supernode. There's a supernode. Do you see that?
At D1 and D2.
So that is the supernode. V1 minus 0 over 6 plus V2 minus 0 over 6 plus V2 minus VT over 10. That's equal to 0. And next one.
KCL at VT.
KCL at VT. VT minus V2 divided by 10 minus 1 is equal to 0. Solve it and give me the answer. Can we? No. I need one more question because that's 2 equations and 3 unknowns.
You can substitute V2 over 6 as your I, and you use the difference in voltage between 1 and 2.
Okay, so first, whenever you have a supernode, you need one equation from inside the supernode, right? So V2 minus V1 is equal to 2I. You added one equation, but you also added one unknown, right? I. So where is I? This is a very critical question. Where is I? Passing through the 6 ohm. Do you agree that I is equal to V2 minus 0 over 6? Okay. Now, solve that and give me the answer. I don't care if it is 4 equations, 4 unknowns. You have to do it using your own calculator. Okay. What do you do in these cases? When you have to do it using your calculator and you have 4 equations, 4 unknowns.
Elimination or something.
Yeah, get rid of I. Instead of I in your equation, put V2 over 6. It will be 3 equations, 3 unknowns. I'm waiting for the answer. And you know that which variable, which unknown in your calculator you're interested in, you're after. I don't want V1 and V2. I only want Vt, right? Pardon me? No, I'm waiting for Vt.
Yep, 13.6 volts.
Can someone confirm? Someone else. From calculator, not from the previous part. Okay. Now, what is RTH? Yes. $13.6 ohms. Was it a wise idea to use nodal for this circuit?
Yes.
Was it? You like nodal?
No,
If you went for mesh, how many unknowns will you end up getting? One.
yeah, one.
Because there are 2 meshes and the right one is known. So it would have been a little easier. Anyone interested in the mesh version of it or no? No? Okay, if you're good. Let's do the next example. Let's find the equivalent resistance from across the terminals. So what do you suggest? Do you suggest test voltage source or current source? Vt 1 volt. This is my IT. Okay. I don't want to forget that critical step again. There isn't any independent sources to remove, okay? So please be careful not to remove dependent sources from the circuit. What do you suggest we do for this? Okay, since we're being stupid, let's do nodal again, okay? Nodal. That's actually a good practice to show you that, I mean, it is a joke. I mean, there's nothing stupid in circuits 1. Whatever you do, the difference is going to be 1, 2 minutes, okay? Now, what's this guy? What's the voltage? 1 volt. Right? And how about this guy? Let's do it a step by step. I know, that's very good. But what do you call this? How do you label this, whatever that color is, purple node? 2i. Is that obvious for everyone? Now, before writing the nodal equations, is there any way to simplify and get rid of that I?
It's 1 minus 0.
So I is 1 over 10, right? One minus 0 over 10, which is 0.2 volts, actually. Now, what the hell did I do? I went for nodal to find some equation based on my unknowns. I don't have any unknowns. Right? So what am I after? IT. Is my nodal going to help me anyway? Writing nodal equations? No. You don't have to analyze the circuit anymore because it's already solved. You have everything. You have the voltages there, 1 volt and 0.2 volts. So if you want IT, what should you write? Write a KCL at the red node. IT is equal to 1 minus 0.2 divided by 5 plus 1 minus 0 divided by 10. And let's see what the value is. I don't know what the value is. I don't have it here. What do I? No, I don't. 0 point? Someone else confirm? 6 amps. So, what is R Thévenin? Yes, 3.85 ohms. So not only it wasn't stupid, it was actually very easy. Nodal. Yeah. Could you please repeat your question? No, because dependent source not necessarily have a resistance representative. Sometimes they do, sometimes they don't. Okay? Any question? Mini lab, please.